We talked about discrete distributions of points or disks, and now today we'll try to somehow connect the dots and provide another viewpoint to those patterns. This time I will be more relaxed in terms of dimensionality, although it will be always in finite dimensional spaces. But I will start with data or point set, finite point set that are embedded in, let's say, RD. And the approach that we will have in this lecture would be the following. We are not supposing anything about the underlying manifold. Our goal is not to reconstruct the data based on some sampling conditions or have any kind of topological guarantees in terms of the analysis that we will have. We will try to just remember some specific building blocks that are used in terms of geometric data analysis. And the big motivation that we will have here at the very first part of this lecture would be clustering. And it's a good coincidence that we talk about geometric data analysis for medical imaging applications. Here you can see some cortical surfaces that were somehow placed based on some metric that were imagined. And you can think of this kind of data where each shape is represented as a point, embedded again in probably high dimensional spaces. And the idea would be to be able to group them based on some criteria and then do what we call classification. So as it was said this morning, we have kind of at least two big categories. We have what we call usually big data analysis, where we would like to have some analysis on, for example, very big social network graphs, etc. Or we might have some more specific and, to my sense, more important in terms of reliability for data classification for example, medical diagnostics. So these, it's just to say that clustering algorithms are important. And again, we are not done with somehow closing this important problem in terms of scientific research. Another thing that I wanted to mention in this direction would be the important, let's say, elements for such clustering approaches. That would be, first of all, in case of big data, the scalability. If we are interested in algorithms and models for clustering, we should be able to handle larger and larger data sets. Another aspect that is quite important is the fact that we would like to be able to integrate some knowledge, some specific knowledge in case of applicative scenarios, as we will just showcase some of those. We are, of course, wishing to handle nicely noises, outliers, and be able to have some kind of interpretation of the kind of results that we have. And for all of these purposes, I think it's very, very important to go back to the very, very basic building blocks of these algorithms, mainly proximity criterions. The fact that we are defining a kind of closeness or proximity between our data elements, each of our samples, and we would like to base our models and clustering algorithms to these proximity graphs or neighbors. So for this, I mean, as for the very first lecture where I had to deal with the very basic geometric element that was point and the set of point patterns, today I would need to talk about some basic elements, mainly Voronoi diagrams and Delaunay reconstructions. You will see, and I will try to really motivate their usage, their nice properties, and convince you that these are indeed the tools that we need to use in many applicative scenarios as in computer graphics. So I think everybody knows about the definition, the classical definition of Voronoi diagram. So I start with a set of points, finite set of points, let's say endpoints in RD, and I will define what we call a Voronoi diagram, or the partition of my space, into convex cells that are defined as follows. The Voronoi cell of each point would be the set of points in RD that would be indeed that would have this specific point as their closest point, right, among all the other points of the data. So obviously, given that for two initial points, if you want to compute this partition, that would be just based on a kind of bisector hyperplane that would separate the two. You can just repeat that, and you can obviously see that the partition that you will have in the Euclidean sense would be a set of convex polyhedra. So these are what we call Voronoi cells. And here is an example in 2D, of course, but you can think of it in any dimension. And the interesting point is that you can define what we call the dual to this partition, or in other words, the nerve of this diagram. That would be the following. Each time I have two sites, 2 points that share, or whose cells are sharing a facet, a common edge in this case, I would connect them to each other. So that would give me a complex indeed that turns out to be a spatial complex. For example, in 2D, that turns out to be a triangulation if your point position is generic, right? If you don't have any degenerate cases, for example, in 2D, 4 points that are co-circular, then you will end up always with the triangulation, which is canonical to this point set, right? So this is the very basic definition that I would need through this lecture. And so the definition of Delaunay triangulation can be also kind of provided in an independent way. If you have a point set, I can also define my Delaunay simplices as the ones who have an empty circumsphere, right? So the fact is that this is exactly equivalent to what we have said, and you can see why. Sorry, I know that it's very obvious for many of you, but it's important to mention the fact that, for example, when you have some of these hyperplane bisectors like intersecting on a point, that in that case in 2D would be the dual to a triangle of my Delaunay triangulation. That would be exactly the point which is of the same distance from the three corresponding red points, and this is indeed the center of the circle, right? So you can think of it in higher dimension, and that would be perfectly true. And this duality is also maintained in higher dimensions. And you know that you have also a notion of orthogonality in the sense that these bisectors are always orthogonal to the connecting edge in 2D. And this is true for any dimension k from, let's say, 0 to d for the corresponding dual simplex that would be of dimension d minus k, right? So these are all trivial facts that I wanted to remind so that I can continue with some basic building, as I said, blocks defined on the finite point sets. Okay, so if there is no question, I can continue. That was just between parentheses, and it's unfortunate that Stefan's talk on reconstruction was canceled yesterday because these are the definitions that I hope to have by Stefan in advance. So I will close the parentheses here, and I will start with some nice properties of Delaunay triangulations. The very first one is that it turns out that these triangulations are studied since years and years ago by mainly in a computational geometry community. We have very nice, robust, and efficient algorithms of different type with nicely studied complexity there, and they are nicely also implemented via the different open source libraries, mainly in computational geometry community. We have SIGA library, which is providing robust implementations of those diagrams and triangulations. The other interesting property that I would like to mention in 2D, that would be a basic property that would give you an idea of why these 2D triangulations, Delaunay triangulations, are interesting, is the fact that if you give me a set of points and you give me an arbitrary triangulation and you try to compare it with this canonical Delaunay triangulation, this triangulation has indeed some nice properties. As you can see, at least in this 2D example, the triangles are much rounder. They are, we are somehow avoiding tiny triangles that would lead us to some numerical errors for many reasons. And indeed, theoretically, it has been proven. It's very easy, not that difficult to prove that indeed this Delaunay triangulation is the one which maximizes the minimum angle over the whole triangulation, or the whole space of connectivities or triangulation that you can think of on your point set. So it's even more than that. If you order the angles of your triangulation in the lexicographical order, you will see that this is also true, in the sense that if you have another triangulation which has the same minimum angle, the second smallest one would be indeed smaller in the case of Delaunay triangulation. There is a question? So you have different. So this is very interesting in the sense that we have different kinds of algorithms. So in 2D and 3D, what has been shown as right? Now, yeah, we have also like the ones that are very interesting that are based on. Yeah, these are the classical ones, and I'm trying to randomize. The randomized ones are very interesting and efficient in 2D, and in higher dimension, I don't want to say any mistake. So it remains. It's the dimension of the. It depends on. Indeed, it depends on the dimension of the ambient space. It's why it's important. It's why it's important to do reduction, dimension reduction, in order to be able to. So I don't want to say it's polynomial, but it's polynomial. It's not exponential in terms of the dimension. I'm supposed to know that. I'm sorry. I will be able to give the right information to you later after the talk. And what is interesting for us, at least in 2D and 3D, is that you can really do it in a very nice manner through, for example, randomized ones. And if I'm, again, I don't want to give bad complexity information, but I think the randomized ones are very interesting. It's of order of n log n, but confirmed later by experts. And these are all in terms of my career, so I'm supposed to know it. But I wanted to say more about this triangulation is the applications in practice. So they are known to be used for mesh refinement, remeshing, and mainly reconstruction, as we can talk about it for hours and hours, because the setting is so that we can nicely provide sampling conditions in that sense. Another interesting property, and it's where I want to start this study, is the one that is highlighted here. It contains the nearest neighbor graph and also contains the minimum spanning tree, in the sense that if you fix the set of points that you have in the beginning, you will be able to find all the interesting graphs that you would need already in the Delaunay triangulation. By paying the price of computing the Delaunay triangulation, you will be able to just retrieve all the interesting connections between dots in this setting. So, and it's good to know that, okay, in terms of proximity graphs, one can think of a parameter that would give you a notion of neighborhood. So these are known as epsilon neighborhood graphs. So that would connect indeed the points within distance epsilon of each other. So it has a very generic definition. Then you will think of nearest neighbor graph just based on the given point set. You will connect the point, each point to its nearest neighbor. So this is another definition. This is what you all know about minimum spanning tree, is also a notion of proximity graph that would just give us the spanning tree over your point set that would have the minimum length h, the sum of lengths of the corresponding edges. And another one, relative neighborhood graph. So that would connect 2 points that indeed for which there is no other point that would be closer to both of them than their mutual distance. So why I'm talking about all these different notations? Because they would indeed provide a kind of nested sequence, this kind of proximity graphs that would end with Delaunay triangulation. Except, of course, the epsilon neighborhood graph that would depend on the epsilon parameter. And these are very classical, used in practice by many people. But there are also other kind of proximity graphs that are less used, I would say, in practice, namely the one that I mentioned here, which is called sphere of influence graph, which is not a subset of the Delaunay triangulation. And what's the idea here? The idea here is to indeed connect 2 points if the distance between these 2 points is somehow small, based on the distances that they have locally, based on their local density. So, for example, we would connect them if their distance is less than their distance to their corresponding, respective nearest neighbor. So this is what I show by NN, distance to the nearest neighbor. Okay, so it has an interesting property, somehow intrinsically hidden in it. It takes into account the local density of the points. And this is where we wanted to start, for example, to revise some of the existing proximity criteria that we knew, and we suggested to have a new viewpoint of this kind of proximity, and saying that, okay, we will introduce this notion of epsilon parameter in it, and by also generalizing the notion of distance that would allow us to change the notion of nearest neighbor here, we would really provide much more flexibility in terms of the graphs that we are considering. Here is an example, and I will give much more details about it. It's just to say that, for example, if you consider for this point set, which is everywhere the same, the Delaunay triangulation, okay, that would give you a structure, a set of connectivity that would contain most of this proximity graph that I mentioned. If you take, for example, KNN, the classical algorithm that you know all, that would give you this kind of clusters where you just say that these points are somehow belonging to the same group. And the nearest neighbor graph would give you also this kind of information. But if you make this epsilon vary and you consider this new proximity criteria, you see that you will have much more flexibility and the connections are somehow different. So what's the idea behind and how we can formalize it? So the idea behind is to simply rewrite everything in this sense and define what we have shown here as a density-sensitive semi-metric, because it's not a metric anymore, but it doesn't matter. We can consider it and use it as a kind of generalization of epsilon neighborhood graph, right? So nothing really surprising here, but it turns out that by integrating some information of topological data analysis, we can make the best use of it. And indeed, generalize the notion of RIPS filtration that some of you might know, to have a better, let's say, setting that would allow us to see other connected components somehow that would appear in this data set. So just to say a few words about RIPS filtration. So given a point set, this is quite classical. You try to grow balls from each of these points, so that would correspond to this epsilon neighborhood graph that we were mentioning, because as soon as two balls are intersecting each other, you would connect them to each other. So that would be somehow the birth of a new connected components. In that case, this is the one that we are interested in. And as soon as a new connected component is created, we will show it in the corresponding so-called persistent diagram. Here you have persistent barcodes. So you will see how during this process, what we call filtration, because you will have a nested set of indeed sets by making grow these balls. So how stable all are these like connected components that are appearing during this process, and at the point where they get merged, they will just, the barcode will end. You will have a kind of death event, and you will try to just keep track of these in general homology classes. So in red, this is the first order. So we are just interested by the first Betty number, but in blue, you will see, for example, the cycles that appear. In this setting, since I'm interested in clustering, I will just look at the trivial part for the connected components. And you see that this would give us a way to see, indeed, the hidden topological structure of the data set. Okay? And by looking at the corresponding persistence barcode, they can just look for the most stable, let's say, for example, connected component that remains. Or if it's the case for the cycles, they can read from this barcode what's going on this data set. That can be very high dimensional and quite complex. And there are some open source libraries that would allow you to do this kind of political data analysis. I'm not an expert, but we have many colleagues who are working on different algorithmic aspects and theoretical aspects. The corresponding, another way of representing this thing is through persistent diagram. Rather than showing these barcodes, I will just show them with two coordinates. So on t, for example, if this is the time, that would be the epsilon value indeed. So the birth and the death time as a 2D coordinate that would give me these points that will obviously, by definition, live on above the diagonal, because always the death appears after the birth. So the ones that are indeed, if you have some points that are very close to the diagonal, it means that these are very unstable elements, right? Because it appears and they die. So somehow the most interesting ones are the ones that appear quite far from the diagonal. These persistent diagrams are very nicely studied. There is a distance that would allow you to compare them to each other. This is called bottleneck distance. So that would be a matching between different points in the two persistent diagram. And there are mainly some interesting stability results, in the sense that if you perturb a little bit in the Hausdorff sense your point set, the persistent diagrams remain stable, remain close to each other. And this is very, very important in terms of robustness of the analysis that you would have. Okay, I will finish with this remark and reminder to say that, okay, we can do the same thing and apply the same machinery rather than using the usual Euclidean distance before. We can now use our semi-metric here in this setting and see what are the most stable components that appear. So since it's a generalization of RIPS, I can show it, for example, on this example, that the RIPS would give us this, but for example, using this new setting, you should be able to see more things, for example, like this one. It would be probably more relevant in some cases, okay? So in terms of stability results, if you are interested, using this kind of semi-sensitive semi-metrics would give us also some similar stability results. The fact is that they are unstable under Hausdorff distance, Hausdorff perturbation of P, but we came up with some stability property through Wasserstein, like by looking at these point clouds as some of Dirac's and consider there in a space of you can see it like defining a Wasserstein distance over the space of point clouds there in order to be able to prove the same kind of stability results at the end. So the stability results somehow can be read at the very end of the slide, which says what? It says that we have a kind of continuity of the map that would map my point cloud to the persistence diagram of this RIPS filtration of this point cloud with the corresponding semi-metric that I considered, which is continuous. Continuous in the topology induced by the Gromov Wasserstein infinite distance on like finite metric spaces. So this is the stability kind of results that we have to say that would be meaningful to use them for any clustering purposes where we want to induce, introduce some flexibility or awareness, sensitivity in terms of the local density. So I cannot show it for higher dimensional space examples, but I will come back to my intuitive stipple art, 2D stipple art examples to show you some results. For example, this is one of the classical density-aware sensitive clustering technique, dbScan, that was compared to these new clusters given by the new approach that I just presented. You see that although there is no perfect or clear distinction between different regions based on that, we are ending with some kind of stable set of clusters in this challenging example. But again, it's just to say that there is no optimal solution yet. For clustering, we all know that we need to apply specific tools depending on the kind of data that we have and what we are looking for. But the flexibility that we are providing here is interesting, for example, in terms of the metric itself. Why not using another metric in the nearest neighbor approach to adapt it to the applicative like scenario that we have? I will come back to my ecosystem analysis or synthesis that I presented last time, where we had the canopies of different vegetation represented as circles, and we had really real data, very simple examples that were coming from biologists to study these ecosystems. We extracted some PCFs and we tried to analyze. But the fact is that the vegetations were already labeled. We knew about the clusters, the category of each of these vegetations. But what about clustering them in automatic way? So that was one of the challenging, problems we have considered in the past, and we didn't manage. But this time with this kind of approaches, since it's just density aware, by using the right metric, that was the metric that I introduced last time, that was adapted to this application context, you are able to find these clusters automatically. So this is where you just grow the value of epsilon to see these clusters appear, and it turns out that the most stable, stable clusters are the ones that are shown on the top, that are exactly the ones that we wanted in that specific case. So, and to finish with this clustering algorithms, I should say that probably this kind of information and flexibility can be also injected to other kind of clustering techniques. It's what we are looking at right now. For example, to some extensions of dbScan, optics, etc. We can easily introduce this kind of tiny tricks, very intuitive and simple, that would maybe allow us to really improve the result of clustering. So, but as we all know and is shown in the current studies, it's very data-driven, data-specific, and we need to always find the right tool to use in the specific context. So we have no final solution yet to this. Mainly, for example, you can see that for even this kind of techniques, although we can do very simple, we have still some improvements, we are far from having something optimal. Another direction that one can think of is to incorporate even more a priori information about the data. I talked about density right now, and you know that in this kind of point patterns, we have another ingredient, which is the correlation between points, which is important. So the correlations, we try to model them through colors, if you remember, for this kind of examples. If you now, without knowing, of course, these things, because we cannot consider the correlation into this approach yet, if we just simply apply the Singh algorithm to see what would be the result of the clustering, Singh is blind to the correlation and can see only the density, that would end up with something which is not meaningful, really. So that would be interesting to give even more information about the correlation, which is another dimension in this point pattern models, to be able to guide this kind of clustering. So that is about the very first part. I always finish with like open questions. These are indeed hard questions, but you can see that with very simple, intuitive geometric ideas, we can still improve slightly the existing methods that are sometimes very old. Yes? For example, yes, that's, but the most stable ones, right? Yeah, so you just study them through persistence diagrams and you try to find the most stable ones. This is one application indeed of this proximity criterion. It was just to illustrate how useful they can be, but it's like any other proximity criterion, you can use them for, I don't know, manifold learning as well, because usually we use classical Near-Sniper to be able to, so you can also try to use them as probably more relevant. So here, this is, I mentioned embedded data, embedded point set, right? So the best examples that I have are in 2D. And in order to show you something meaningful, I need to come up with a point set that is representing something. So I always represent them in the context of steeple art, but there are, of course, some specific objectives here. Why we are interested in this kind of segmentation, etc., etc. It's again for some very precise application in terms of, as I've shown, tactile point patterns, automatic generation of tactile point patterns, art design, etc. So even in 2D, they are interesting, and I make the best use of them as toy examples for the kind of algorithms that we have. Yes? Of course, it's always. So in which sense? Of course, there are different clustering algorithms, and one would be able to probably, for example, put more, make a combination, put more importance through weights to one of these clusters, and so this is something that can be done. My very naive answer, the second one that is maybe that does not maybe make sense in general to expert in TDA would be the following, because as I said, we are studying the most stable clusters through some criterion that I said on TDA analysis. There are multi-parameter TDA methods as well, so where you can just do it through different. You see the robustness of your, like the creation of your homology classes based on different criteria, and you just analyze them in a kind of mixed manner. So these techniques exist. I'm not an expert, but definitely there are ways to combine them. It's somehow density aware, density sensitive, and one can see it as a. Maybe I can just, it's not so difficult, maybe I don't need to really write it, but usually we take 1 over the distance to the nearest neighbor and a density estimator, right? And so here we have 2 density estimators corresponding to each of the 2 points that we have. So you can take, for example, the harmonic mean of the 2 density estimators. So that would be the harmonic mean of the 2 density estimators would be this, and you are somehow multiplying that by the distance between A and B, right? So it's a new density estimator that you are considering. If you take, this is a density estimator, right? The classical one, right? So now you are somehow taking the harmonic mean of a classical density estimator, and we're trying to generalize your, nothing surprising. But once you talk with like experts in this domain, for example, my colleague Steve Udo helped us a lot in terms of formalizing these things. Yeah, it was in, for sure. It was in the first lecture. So the way we see it is using, so of course, you can go through power spectrum of these noises. For example, if it's blue noise, pink noise, etc. Power spectrum is always a way to analyze them from from Fourier-based approach. But the way we see it, at least in many of our works, is using pair correlation functions. It's a kind of average density estimator. So starting from, I don't know, starting from a point, I grow circles around my point and see how many neighbors I have at radius r. That would give me a graph that I can average. So I can normalize based on the density. I can play with this kind of like signatures. I talked about many things, but I would like to showcase the applications. It's why it takes some time to introduce sometimes quite simple notions, but I'm happy to take questions about it later. And it will be hard, but I will do my best. So anyway, I knew that I had to just go through the space of triangulation and properties, and will not have time to do the very two last parts that will be done, hopefully partially at least on the third lecture. So I talked about proximity algorithms. I talked about the way we connect these dots, but usually we are interested in more structures, like we are looking for example, in terms of reconstruction, we are interested in simplicial complexes to define nicely a kind of piecewise linear surface that would somehow form an approximation of probably an underlying manifold that is from which these points were sampled, right? So, and the very classical, tool that I already introduced are these Delaunay triangulations and the dual structure Voronoi diagrams. And here is where we can, like little by little, go toward circle distribution, circle patterns, etc., and circle packing at the end. So the idea is to say that by adding just a scalar to each of the points in Rn, I can just generate a new data set that would be a set of circles, right? Or spheres, the dimensions. And the idea is to say, okay, how to now adapt this new this partition to this additional information, just a scalar, nothing else. So the idea is to just add an additive weight to the Euclidean distance that we had before to define what we call weighted Delaunay, generalized Voronoi diagram, usually called Laguerre diagrams or power diagrams. And there is a specific reason for which it's called power, because it's somehow the power with respect to the corresponding circle. And the corresponding dual would be something that we call weighted Delaunay triangulation. Sometimes it's called regular, and I will explain why they are called regular. So I'm presenting this as a set of circles, but please note that these weights can be also negative, right? So I'm illustrating them as positive weights, but they can be also negative, but I cannot show them as circles here. And the fact is that, again, under some generosity conditions, it's always the dual is also a set triangulation. Okay, and these triangulations have a very nice property that some of you might know. First of all, you might know it for Delaunay triangulation. The fact is that if you give me a set of points, let's take the 2D case, but it's true for d-dimensional point set as well, I can just, in order to find the connectivity induced by the Delaunay triangulation, I can lift my point set to dimension rd plus 1 on the paraboloid, y equal to x squared. And then, so that would give me a set of points, and then I will take the lower envelope of it and project it back to my space. That would give me a triangulation. And this is indeed a particular case of what we call regular triangulation. Any triangulation that can be indeed presented as the projection of the lower envelope of a convex function is called in general regular triangulation. And indeed, we have the same lifting property for the Voronoi diagram, which is the dual to it, which is the following. Rather than just, you lift your points on the paraboloid, and you, rather than taking just the lower envelope, you would just take the tangent planes to those points, to the paraboloid, and that would give you, again, another envelope that you can project back, and that would give you the Voronoi diagram. So this is a very interesting notion. And when you have the weighted version, you can just simply shift up or down the tangent planes that you have with the same orientation. That would give you a different lower envelope. If you project it back, that would be the exact power diagram, and the dual would be the weighted Delaunay triangulation. So you can say that, okay, by doing this kind of shifting, if my weights are like, so if it's minus the weight. So if my weights are too small, they may just go so high that they will not appear on the lower envelope. Yeah, it's true. If the weights are, the distance between the weights are too large, then you might have some of these circles that do not have any dual self, and they do not appear in the Delaunay triangulation. Sorry, long story short, this is a very interesting property that was used even for mesh optimization, for example, by minimizing the distance between this piecewise approximation of the paraboloid by the two corresponding lifted diagrams. You can improve the quality of the mesh and its dual. These are known as centroidal Voronoi tessellation. So there is a variational method. There is this error that gets minimized, and it leads to very nice triangulations, and also optimal Delaunay triangulations, ODT. There was also an extension that was proposed a few years ago by my colleagues. It's not one of my work, where you just use the Hessian of convex functions in order to introduce some kind of anisotropy to your mesh and optimize based on the anisotropy that is given. I will not go through this because I'm just interested for the moment in this lecture, in the combinatorics or connectivity between the points. So I will, in the time that I have that is left, I will try to talk about the space of triangulation. Okay, and this is an interesting property that you might not know. So here is the beginning of this study. You will have a set of points that are given, finite point set in RD, and you would like to see what are the possible connectivities that you can consider in terms of triangulation. So you have seen this example. These are two different triangulations for a given 2D point set, and I can think of many of those. It's a finite set, and I'm interested in studying this space of triangulations. First of all, there is an interesting mathematical property that is known and is not yet perfectly used in our community, but I will mention it, maybe that will talk to you. It's the notion of a secondary polytope. It turns out that when you consider this set of endpoints in RD, you can associate to each of these points for a given triangulation the volume of its incident simplices. Okay, that would give you a value per vertex for a given triangulation. So I will put it in a vector, so that would be an n vector, and I will lift this as a point in Rn. So my points were in RD, but I had n points, and this point that would represent a triangulation now would be indeed in in Rn. And the funny thing is that if you consider all the possible triangulations of that given point set, that would form a point cloud, of course, on this weird high-dimensional space. And if you take the convex hull of this, indeed, the vertices of this convex hull are exactly the regular triangulations. It's very surprising. It's quite hard to prove and imagine. And it was done by mathematicians in another field, indeed. But it's very interesting. It shows that these triangulations are very specific and have some amazing properties. And it turns out that these are exactly linked and are these weighted triangulations. So, and this is what I would like to mention in the following slides. So, in order to talk about it and formalize it, I will just introduce two more definitions. First is the fact, on the fact that I'm interested by the combinatorics of it. So I will define dual complexes, like you can think of Voronoi-Delaunay, but in a combinatorial manner, saying that I would say that these two complexes are indeed dual to each other if they induce the same combinatory, like connectivity between the points and the corresponding cells. So, and so in this setting, since everything is combinatorial, they don't need to be orthogonal to each other. They, each point does not need to belong exactly to its cell, etc. But it's just a compatible combinatorial setting. And the fact is that it has been shown that any pair of orthogonal primal dual triangulation, in this sense, is indeed a regular triangulation, which is a power diagram, one of the notions that we have mentioned. That was shown quite a long time ago, and now what we are interested in knowing is to say, okay, we know and we can characterize, thanks to this result, orthogonal ones. What are the non-orthogonal ones? And just to give you an idea of how it was proved, it's really based on finding like consistent lifting of the hyperplanes to be able to, at the end of the day, combinatorially satisfy the connectivity between different cells. So the proof is somehow intuitive and understandable. And now we are kind of interested by the non-orthogonal version of it. And the interesting thing is that the non-orthogonal ones are exactly the ones that are seen as perturbation of regular triangulation. They are combinatorially equivalent to a regular triangulation. In other sense, for any compatible primal dual pair of triangulations, there exists a regular triangulation such that this is the complex that we are considering is dual to a perturbed regular triangulation. And this gives us a way to parameterize the space of triangulation and do an interesting thing in computational in computer graphics. Before I go to the parameterization, I will just mention two other properties. The fact that in 2D, indeed, any two-dimensional triangulation can be perturbed in a way that we end up with a regular triangulation, just it's combinatorially regular. And the fact, which is very surprising to me, is this one is the one that for dimension more than 3, I mean, there exist triangulations that do not admit any compatible dual in a combinatorial sense. And there are some counterexamples that are given, so I would refer you to our paper to see them, but it's quite hard to imagine, but and it's linked to the notion of Schlegel diagram, which is equivalent, but nothing important. So based on what we have said, we have now a parameterization of the space of triangulation, saying that I can just represent them by the position of the points, by the weights that are given, and also a kind of displacement vector that would somehow perturb them. And that would completely characterize and parameterize the space of compatible primal dual triangulation. It is what we have used for for our mesh or optimization in particular applications, because that would allow us to have a kind of independent manipulation of primal and dual complexes. How do we do that? It's simply by adjusting, doing an optimization, for example, based on a variational technique, an energy that we have to minimize to optimize the position of primal vertices and to optimize the value of the weights to position better the dual complex. This was indeed the link to the circle packings that we will see in the last lecture. And I will end up with two more examples here. For example, here, showing that based on this optimization of weights and position of the meshes, for example, we can have some interesting numerical approaches that would improve the numerical performance of some of our computational tools, such as, for example, Laplacian, that would depend on both primal and dual structure, because as you know, Laplacian operators on meshes are mainly based on this cotangent formula that can be represented as a relation between the dual and primal structures. And so by keeping the mesh as is, without changing to the initial primal mesh, I can adjust the scalar, the weight that would move somehow my dual structure in order to make this dual structure, my triangles, well-centered, that would improve the numerical stability of my Laplacian, and that would be interesting for some discrete analysis of my simulations somehow. These are the references that would go with this part, and I will finish with this by jumping to the final references acknowledgement. I had another application to show based on the capacity constraint property of regular triangulations, but I will leave it maybe for another opportunity. Thank you very much.